All right, hell yeah. So we're going to continue on. This is section 5.4. What we're doing is beam bending. We're going to read textbooks. And hell yeah, the textbook that we're reading today is Material Mechanics. This is James M. Gear, Barry J. Goodnow. All right, hell yeah. So let's see where we're at. Okay, so we're doing longitudinal strains and beams. I've already covered the introduction, and then the first two sections. So let's just do a quick overview. So if we have a cantilever, we can pull up on it. The take-home point is that if this was a slinky, you know what I mean? Each disc of a slinky would move up. That's shear. But what happens is that we don't get a lot of deflection. You know what I mean? This visible height right here is this letter V, small v, for the deflection in the y direction. And due to the shear forces, that's just not very much. But bending is hella, you know what I mean? And we prove that, I mean, basically from just taking a small little slice, and I like to think of this as almost a square chunk. Like, let's say the beam was only 4 molecules of iron, you know what I mean, 2 tall, and then we're just taking 2 molecules. This moment has to be, and the take-home points are: a moment is a force. It's a load. It's 2 opposing forces. So to generate this moment, I got to apply a force arrow this way and then a force arrow this way. So they're 2 opposing forces with a distance between. And what's going to happen is these two, this side is going to have those same 2 forces, a force this way and a force this way, and kind of just equal and opposite directions. And if this moment goes this direction and this moment goes that direction, this is what we call positive. Like we would say these moments are both positive, or causing this thing to smiley face. You know what I mean? They're not. This moment's not opposed. Anyway, so if you want something to bend in a shape of a smiley face, you have to apply this arrow in that direction and then this arrow in that direction. You can do this to a ruler. Cool. So the 2 forces on the top 2 molecules crunch in these molecules, and then they stretch out in tension the bottom 2 molecules. And so this vertical line now becomes angled. And so that's going to be today's topic of figuring out like how much these 2 do get crunched in, and how much do these 2 actually lengthen. And if this part of the beam gets crunched in and this part of the beam lengthens, there must be a line, this dotted line, where it's neutral. You know what I mean? If I started with this width right here, we're going to call that dx, and then this top part reduced in length, and then the bottom like stretched out in length. But there must be a line that did not change length, and we're going to call that dx. And we're going to pretend like we don't know where that is. You know what I mean? And so it's at the centroid, and that's why you use a cross-sectional shape like this, where your centroidal axis is just a little bit lower than the halfway point, and it kind of shows that better. Okay, so, but back to the take-home point. If this line, because these 2 molecules crunch in and these 2 stretch out, if this line goes from vertical to slightly angled on this side and slightly angled on that side, like, hey, we have a segment now that actually has, these 2 lines are going to come up to a point and touch, and the angle between is going to be d theta. And with a little bit of, I guess, I mean, I would want this to be common sense, but this is not. It's kind of difficult to see, where if this angle creates d theta, that means that if I take a tangent line right here, or just pretend like this one is the cantilever, like welded up against a wall, and then this part is higher because it's starting to curve up, the angle, if this angle is flat at 0 degrees, this angle's tangent will be d theta. So whatever angle is right here is also the angle that this one increases by. All right, hell yeah. Oh, damn it, the TV's going in the other room. Let me turn that off. All right, hell yeah. So we're back, and I'm glad I took a little break because this part isn't so intuitive to me. But if we have a constant moment, and you can do this with a flexible ruler, you know what I mean, twist the ends with your fingers, and then all throughout that ruler you're going to have that constant torque due to the moment that you're applying at the ends. And what we get when we have constant moment is that at each cross section, so we took those 4 molecules, these 2 lines became angles, and then if we just move over another 4 molecules, that same thing is going to happen. And so from here, we're going to get a curved shape. And like I just said, if we make this line vertical, and then this line is the one that's angled, this will have a tangent of, let's say, 0 degrees, and then this will have a tangent of d theta. And then we can do that same process over again, and we can also just visualize this also to be vertical, and this line to be the angled one. And so, and again, this tangent, if we set this tangent angle to be 0, that this tangent will be d theta. So, so that's how bending. So I guess the take-home point is that bending creates big deflections because in between every 4, 2 rows of atoms, you're getting them to crunch in at the top and lengthen at the bottom, and you're getting a small change in angle to form. And that's going to be each little slice of this beam is going to continue with that change in angle. And this is the definition of a circle. Like this arc makes a circle, and that's where from mathematics I have a hard time, you know what I mean. But now I kind of understand is like because we just showed 4 molecules here in this square, and then over here 4 molecules, and they're getting crunched in and stretched out the same. And if we just reset our origin of this line now. I should just go to chapter 9 because they have a picture of it. So I'll do that right after this. But so the take-home, I shouldn't say take-home point all the time. It's so dumb. But anyway, so if I have a tangent here, whatever angle this is, you know what I mean? And it even looks like negative, 2 to 3 degrees. And let's say, and this angle looks like positive 2 to 3 degrees. So that means that this has to be about 6 degrees. So however this tangent changes to this tangent is because of this d theta. And so if I say this angle is about 3 degrees, and then I say this angle is about 9 degrees, it's because the same thing happened. The angle in between here is 6 degrees. So let's go to chapter 9, and just because they do and this book is a little bit all over the place, but it kind of makes it fun. Maybe not, because it's kind of hard to put everything, but here you go. So here's the better look at a curved beam, and this is the chapter on deflection, where right here is what I was talking about. Like from the horizontal, the tangent right at this point, let's just call it 1, M1, the slope is going to be this angle theta. Now at M2, we're basically going to have theta. You know what I mean? The slope doesn't change too much. So it's going to be theta, but it's going to be this this plus the change in angle. So that's where we get that d theta. And that d theta is this arc, this part of the arc. So we have a curved line. This is a portion of a larger circle, and then that circle meets at the middle, and this little segment, whatever angle this is of that circle, is how much this angle changed from here to there. Okay, so let's go back, and because this is this is not pure. You can have a cantilever with generating a pure moment at the end. So, you know, if there's no loads on here, sure, you can just apply a moment on this end, and that moment's going to be the same throughout. And this whole thing, if that happens, if you have a constant moment, this whole shape will be an arc of a circle. We'll go back to the example that we had. Right here, we don't have a pure moment on this cantilever. We have typically what happens with a cantilever, you're applying a load on it. You know what I mean? An upward or downward force. We're just applying an upward force because our deflections are going to be in the positive y direction, even though most things will have deflections in the negative y direction. The reason why we're doing this also, this is a smiley face up, so our curvature is positive, and we'll get into that today probably as well. But cool. So here in this diagram, we're going to have most our moment is at point A. This is going to be our biggest portion that has the moment. There's going to be no moment at point B, no moment generated. And so you would figure out those from the shear and moment diagrams. So I'm probably not going to go into that, but yeah, just this force causes the biggest torque about point A, and actually about point B, it doesn't cause anything. We have a linear line right at point B. If I came right here, this circle would be huge. Compared to point A, you'd have a smaller radius of a circle, even though this picture doesn't do it justice. All right, so because we have a constant moment, now we can get back to that. This is the arc of a circle. A circle always changes the angle at a constant rate. And so if this is the portion of a circle, here's the tangent line of a circle. Let's say it's negative 3 degrees. I'm going to move 6 degrees down the circle. Well, heck yeah, now the tangent of this is going to be positive 6 degrees. Sorry, positive 3 degrees. So that this would be, if this d theta was 6 degree change, then right here the tangent would be negative 3. We would add negative 3 plus 6. We would get positive 3. If the same thing happens from here to here, I go from positive 3 plus 6, and then this tangent must be 9. And even that is just like mathematically going around a circle and doing that, to be like, really? And does that make sense? Because if I had, let's just draw an imaginary circle, and I'm right at the bottom, my tangent is 0. Let's go all the way up to 90 degrees. You know what I mean? So if I sweep out an angle of 90, does that mean my angle changed? So if I come here to be to the tangent, heck yeah, the angle is 90. So I do this with a lot of math equations. It's just like, well, let's just pick a bunch of points and see if this actually makes sense. You know, I could even go all the way around the circle. I could do an angle of 180, and yeah, the angle changes from 0 to upside down 180. You know what I mean? So, all right, booyah. Okay, so that's going to be kind of our introduction. So let's start reading some text. All right, so we got longitudinal strains and beams. And so yeah, this section is going to be about the change in lengths. So we want an equation for that. We know at some point there's a place where nothing changes. This line is still dx. Even though it's curved, its length is still dx compared to an uncurved, unloaded beam. And so what we want is an equation. We're going to say y is the positive direction. And when we move in the positive direction, our length should decrease. So if we throw in a positive value of y, we should get a lower number. So if we start out with dx, even from a mathematics, you know what I mean? Even if we don't know what the equation looks like, it should probably look like dx. Because if we're at y is equal to 0, we should have dx and then maybe minus, y dx. You know what I mean? Just even that and plus a constant, you know what I mean? But on the y part. Because if we're at y is equal to 0, our length should be dx. If we were at y is equal to just right here, we would have dx plus, some sort of a proportion related to this value dx. And so that's what we're going to get. Cool. All right, so the longitudinal strains in a beam, and strains are the change in length. So when we curve it, the top crunches in, that shortens in length. So that's going to be a negative change in length. Strain, for the value, is a proportion. It's the percent. Yeah, that's a great way to think of it. It's the equivalent of me calling sines and cosines percentages of the hypotenuse. If you have a right triangle, the hypotenuse is always the bigger number. If here's the sine component, maybe the vertical component, it's always going to be smaller than the hypotenuse. So we're always going to take the hypotenuse and then multiply by a number, like sine of the angle. And sine of the angle is going to be theoretically a percentage. It's a fraction of the whole. But I like to think of it as a percentage. I think people just have a better idea with percents than fractions. So strain's the same thing. It's going to be the percent change in length. And so yeah, that's a great way to say it. So if the change in length was 1%, you know what I mean? Hey, maybe it got 1% bigger. I can visualize that. So let's say the change in length was negative 1%. It actually got 1% smaller. We can visualize that. And we can probably just do a very simple equation that makes sense. That's the equation for strain. Just for our problems or material mechanics, for steel, this number is really small. It's going to be 0.2%. But still, that ain't bad. We can visualize 1%. Now we're, decimals, fractions and decimals. It's really difficult to wrap your mind around fractions and decimals. So steel, the max change in length would be 0.2%. After that, you got problems. Okay, hell yeah. And I'm glad I'm going over that because this term is the heart. It's probably why I failed this class the first time around. Strains and shear stresses is just like, yep, I'm done. Anyway, so the longitudinal strains in a beam can be found by analyzing the curvature of the beam and the associated deformations. Okay, sweet. So this is kind of cool where if we do have a curve, then and we have that three-dimensional shape, again, if we're saying that this is a line that has not changed, it's going to be neutral compared to this original square. So we are saying the top is getting smaller, the bottom's getting larger. And yeah, this is just the shape of a circle. And so it should be pretty simple. If this is my y-coordinate right here, starting from here, 0, and I go up to this full radius, then at y is equal to this radius, we can call it r or rho. They call it rho for this. You call it r if you want. When y is equal to rho, my distance, my dx, or this length is 0. So just right there, I'm getting better at making equations. So I would say if y is 0, my length is dx. But then if y is equal to rho, my length is 0. And it's going to be linear. We're going to have a linear equation. If I go halfway, if I go, half this radius, rho divided by 2, what's my length? Well, just even look at here. This is the triangle, and if I go halfway, the length is going to be half of dx. This would be dx, this would be half of dx, this would be 0. So just right there, I think I could come up with an equation. It would be the length of this line is going to be dx minus y divided by rho dx. And so that's essentially what we get. This length is going to be dx, that original length, minus y divided by rho dx. That's one quick way to get there, is just to... and then so we throw in a value of 0 right here, this goes away, and our length is dx. If we throw in a value of rho, we're going to have rho divided by rho. This would be 1. And so we have dx minus dx. That's 0. And if we can go the other direction as well. That's why if we're calling this positive curvature, I'm going to say my rho value, my radius, is a positive number. If I have negative curvature, all I have to do is say, hey, the radius, that rho, is in the negative direction. I just put a negative value for that radius. So if you have problems where you're just like, ooh, this has a negative curvature, we'll just throw in a negative number on k, and k, the curvature formula is just 1 divided by the radius. So if the curvature is negative, it just means the radius is negative. And if you set your axis always to be positive, and the x direction always to be to the right along the beam, and negative curvature means that your radius of curvature, that rho, is always going to be in the negative y direction. So you're going to have a negative radius for that. So that's one way that you can make sure the sign convention works out. Cool. So then if I go down if I said y was negative rho, doesn't dx double? Shouldn't it be 2 dx? And so that's what we're going to get with this equation. If y is 2 times rho, we have 2 rho divided by rho. That's just 2. So we get 2 dx right here. So we have dx minus 2 dx. And see, I did that wrong. So y would be negative rho. So that's where this value on y does have a positive direction and a negative direction. So keep that in mind. And especially when we're trying to find the stresses, above this line we have crunching in of the beam. That's going to be compression with a negative stress. Negative numbers for the PSI, the pressures that are attributed to that, the stresses. Stresses are the pressures. And then if I throw in a value of negative y, we have tension, and so everything's going to be getting ripped apart. Those are going to be positive values of pressure. And so that's just the convention we use, because even, you know what I mean? I mean, if you're going deep sea diving, I don't know if I would call that negative pressure when you're all just hella crunched, you know what I mean? But for solid mechanics, we're saying that things in tension, that's going to be positive pressure. Things that are getting ripped apart, that's positive pressure. So, yeah, it's kind of fascinating, which would be the equivalent of actually going up into outer space. You're going to be, you know what I mean, your molecules are going to be pulled apart, vacuum of space. Okay, so, yep, so that just shows that the equation that we're going to get is going to be a function of y. You know what I mean? It's always a function of y at this neutral axis. We don't know where that is yet, but if I throw in a negative value, then I can find, you know what I mean? Hopefully it gives me a positive value for the pressure. And so we're going to see that. Not today, though. Today we're just worried about the change in length. So if I throw in a negative value of y, this length increases. So let's go back and fix my mistake. If I throw in a negative rho, so here I said if I threw in a positive rho, this length goes to 0. You know what I mean? And then if I throw in a negative rho, it should double. So if I throw in negative rho right here, I'm going to have negative times a negative. That's going to be a positive. Rho divided by rho is 1. So I'm going to have dx plus dx. And then I get 2 dx. Okay, sweet. So this equation's working out. All right, so let's read some more. All right, hell yeah. So for this purpose, let us consider a portion AB of a beam in pure bending subject to the positive bending moments. And this is figure 5.7a. Is that the one we've been looking at? Hell yeah. So we got figure 5.7a, and we got 2 moments. And so that's what we're looking at. We assume that the beam initially has are we in the right section? Hell yeah. We assume that the beam initially has a straight longitudinal axis, the x-axis in the figure, and that its cross-section is symmetric about the y-axis as shown in figure 5.7b. So right here we have a constant cross-section. We call that prismatic. If it wasn't prismatic and it didn't have a constant cross-section, we might call that tapered, or we would unless the cross-sections were abrupt. Cool. So that's figure 5.7b. Under the action of the bending moments, the beam deflects in the xy plane. So yeah, that's why textbooks are difficult. So we have this the y-axis, x-axis, and yeah, all the bending, the smiley face, is in this xy beam. We don't get any curving out into the page. And always if you're only given a 2D axes, you know what I mean, draw in the third axis, and you do that using your right hand rule. So you start with the lower. So if it's an X, Y, Z axis, you always start with the lower letter, or you just go from X to Y, Y to Z, and then you repeat Z to X. And if you do that, you're always going to get the positive axes. So that's also the same thing with the cross product. If I cross this X axes into Y, I get a positive Z. Y into Z, I get a positive X. So you would put your fingers in the direction of X with your palm facing up, and then you would sweep 4 fingers into the direction of Y, and your thumb is going to be facing this positive Z direction. Do the same thing. Put your palm facing out of the page, and 4 fingers up, and then sweep them into the Y direction, and your thumb should be pointing to the right in the positive x-axis. And then same thing, fingers in the Z, sweep them into the X, your thumb should be pointing up. So, and if you did it in reverse, if you went X swept into Y, your thumb would be pointing in the negative Y direction. And so, yeah, it's just good to do those, because something like that is like, well, just do it the 6 different ways you can do it. So we did X to Y, Y to Z, Z to X. And we got positive, our thumb was pointing in the positive axes. So if we do it the other way, fingers in X, sweep them into Y, heck yeah, my thumb is pointing down into the J. So if I put my fingers in the Z direction and then sweep them up, palm facing, you know what I mean, sweep my fingers, and I guess, yeah, you can't bend your fingers backwards. So the right hand rule is you sweep your fingers forward from Z to Y, and for sure, using my right hand, my thumb is pointed in the X direction. And then, the negative X. So now we're doing it in reverse. So if I go Y to X, sweep my fingers from Y to X, my thumb will point in the negative Z direction. Cool. And so, all right, sweet. Let's read on. Yeah, so things deflect in the XY plane, the plane of bending, and its longitudinal axis is bent into a circular curve SS, figure 7.5c. So anytime you have a textbook, it's just good to actually look at this and almost memorize this figure. Okay, 5.7c. So the next time I read it, then I have just an association of this picture. And we have a section of beam from section S to S, and then we're going to be talking about this subsection in a moment. Sweet. So this conclusion, where are we at? 5.7c. The beam is bent concave upward, which is positive curvature. And we kind of talked about that. Curvature is the equation of 1 divided by the radius that forms from the curve of a curve. And if we set our y-axis always up, and then our if it's our radius, if our radius rho is a positive y value, then we get a positive curvature. We get a positive value for the radius, and because curvature is 1 divided by the radius, we get a positive value for curvature. And I said that if this curve was this direction, I still put my y-axis up, but that means where this radius and the origin, because right here, if this is part of a circle, the center of the circle is going to be up here. That's point O prime. If we have a negative curvature, this little section is going to be a piece of a big circle, and the center of the circle is going to be down here in a negative y direction. that means the radius, rho, to that the circle down here is going to be a negative number. And so a negative number in the curvature, so we have negative rho. And so if I throw in a negative number here, I get a negative curvature. So that's what we have here, positive curvature, negative curvature. All right, sweet. Okay, so yeah, the beam is bent concave upward with a positive curvature. Yeah, it's just kind of fascinating walking your way through textbooks, because I'll just space out reading it. That's 3 sentences, even just 2 sentences, and there can be a lot, a lot to understand even just in that. Cross sections of the beam. All right, so now we're going to talk about this section MN and PQ. So we're going to go and look at that. So we have MN and so MN and PQ. So they're saying that section. Sometimes they go in a full square. They might call this MNQP. But they're going to say we have 2 sections. One section is M and N. And then we have another section, P and Q. These are 2 different slices. And we're going to have a distance dx between them. All right. So such as sections, so let's read this, cross sections of the beam, such as sections MN and PQ in figure 5.7a, remain plane and normal to the longitudinal axis, figure 5.7c. So when we do have bending, all the bending is in the x and y axes. So that's just another way to say that. Oops. All right, the fact that the cross sections of a beam in pure bending remain plane is so fundamental to beam theory that it is often called an assumption. However, we could also call it a theorem because it can be proved rigorously using only rational arguments based upon symmetry. And there's some references in the back. Those are just articles that you would have to go look up. So that's kind of the bummer about these references. The basic point is that the symmetry of the beam and its loading in the figures that we're looking at means that all elements of the beam, this figure is the undeformed, and this is the cross section. So it's kind of fascinating to get used to being like, okay, this is the B portion, that's the A portion of figure 5.7. This is the C portion. So even just kind of reading textbooks, yeah, that's good to, that's what I've been working on, is just halfway kind of memorizing, because it says the basic point is the symmetry of the beam and its loading is that unloaded portion and its cross-section means that all elements of the beam, such as the element, and so now we were talking about the cross-section MN and then PQ. So MN, if we do that from memory, was here MN, and then we had PQ. So they're saying this element is MPQN. So this is cross-section MN, this is cross-section PQ. This element, starting from this corner, we're going to label it MPQN. So that is kind of interesting, just from, and that happens quite a bit when looking at elements. So so this element must deform in an identical manner, which is possible only if cross sections remain plane during bending. Figure 5.7c. And that's that curved shape. This conclusion is valid for beams of any material, whether the material is elastic or inelastic, linear or nonlinear. Of course, the material properties, like the dimensions, must be symmetric about the plane of bending. Note, even though a plane cross-section in pure bending remains plane, there still may be deformation in the plane itself. Such deformations are due to the effects of Poisson's ratio as explained at the end of this section. So what that's saying is that if this gets crunched in, what we know about things that get crunched in, they're going to widen. You know what I mean? If I have a small little cube of material and I crunch it in, it's going to be bulged all along the outer surfaces that aren't being compressed. And same thing here. If I'm in tension here, that's going to make everything suck together. So what we're not seeing is the thickness of this beam. Let's say it has a height h, and it has a thickness b into the page. Because of this compression, that thickness into the page increases, and because of this tension, that thickness into the page decreases. And I did purchase the Hibbeler Material Mechanics book, and it's kind of interesting. One thing I do not like about it is the pages are a little bit dingy. Like, this book just has really bright pages. Like, the white here is the same as in the in the book that I have, and it just makes everything pop really well. So it's really hard for me to get into that book based on that. It's just so fascinating. I mean, it's different too. I'm just not used to it, but that can make it frustrating. It feels like you're in a dark room reading that book. So hopefully they got brighter pages as the editions went on. But I mentioned that because that other book, they do a lot more diagrams. They're not as crispy as these, but I would say the arrow diagrams of things like that, they do show that. They show, a beam that's narrow down here and then widening at the top. And so that's kind of cool to see. All right, hell yeah. So we have that segment. We're talking that everything bends in this direction. But we do have properties like Poisson's ratio that might deform it side to side. But that doesn't mean that it's bending out into the page. Due to this moment, it's not like all the bending is happening in the y and xy axes. Cool. Because of the bending deformation shown in that bending diagram that we're looking at, 5-7C, cross sections MN, that's the one on the left, and PQ, they rotate. So that's what we were talking about. Those lines are no longer vertical. And this is just like, what's the proof here? That a moment causes a curve. But that's why I definitely like to go back. I think it's very useful to put 4 steel atoms, and this moment has to be a load. It has to be 2 opposing forces, and if I just have 4 steel atoms, the forces can only be axial through those atoms, and that's an that's the only place that I could put a force is at the center of mass of those atoms. So there you go. I got a compression force on the top 2 and then a tension force on the bottom 2. And so that's a great way to explain why these lines are now slanted. So these sections, MN and PQ, rotate with respect to each other about the axes perpendicular to the XY plane. Longitudinal lines, that's going to be horizontal lines, on the lower part of the beam. Cool. So now it's just kind of reading textbooks. Can we visualize that? What do you think they're going to do? They're going to lengthen. We've been talking about that. Of the beam are elongated, whereas those on the upper part are shortened. Cool. So it's also good just to kind of mentally stay 2 steps ahead of a textbook. And that's where it's just if you get to a figure, go to that figure. Even if it said right now, hey, in chapter 2, section 2.1, there was something going on, you should just instantly go there and then maybe spend that day reviewing that section. Cool. All right, so the longitudinal lines, yes, the lower part elongate and then the upper part shorten. Thus, the lower part of the beam, the one that's elongating, is in tension and the upper part is in compression. And And even just that sentence, this is the heart of material mechanics, is if I have a chunk of steel and I pull on both ends, it lengthens. And I can read the force that I applied. So I'm going to apply some force, and then I'm going to measure the amount that it lengthened. I double the force, it's going to lengthen twice as much. As long as we're just putting loads that the actual material can carry without causing it to bend out of shape. Where the stresses aren't going to cause permanent plastic deformation. Cool. And so that's the heart of material mechanics, and that goes even unsaid. They should just keep explaining that I don't have to pull on steel with a gauge that says, hey, this is how many pounds I'm pulling. Well, what comes first, the chicken or the egg? Like, you have a chunk of steel, a length of steel, and then you pull 100 pounds on it. And then with electric gauges, just because the distances are so small, you can measure the distance, so you can measure the change in length. Cool, and you say this much change in length happened at 100 pounds. Let's double it, and then you realize, oh, I have twice as much change in length. Then you go to 400 pounds, and then I got twice as much. Then you go to 800, got twice as much as that. And then you just have this linear relationship up until where bizarre things happen. With steel, it just turns into Play-Doh. But we have plenty of strength up to that point. So we just make sure we don't exceed that point. And we don't need to know that we applied 100 pounds. I can take another specimen that's the same dimensions and then just pull on it with an unknown load and then measure how much change in length. And if I measure the change in length, that is synonymous with the load that's being applied. And I think that goes under whatever. It just goes overlooked when learning about material mechanics. I think we are all familiar with like loading things and knowing how much force I'm going to apply, like how much weight in the back of a pickup truck you're putting, how much tension on a climbing rope that you're pulling. But the opposite you would just never do. You wouldn't be like, oh, well, let me see the stretch in that metal steel cable, and then I'm going to tell you how much tension is on it. We just don't do that, but that's a fundamental property of learning about material mechanics, is knowing one, you know the other. And so what we're doing is we're going to measure the change in length, and hell yeah, that's going to give me the tension in that part of the beam. And cool. So, all right, thus the lower part of the beam is in tension, the upper part's in compression. Whereas between the top and bottom of the beam is a surface in which the longitudinal lines do not change length. So we talked about that. I mean, it just physically has to be the case. If the top is crunching in, the bottom stretching out, in the middle somewhere, you have to have a place that does not change length. Doesn't mean we know where that place is. This surface is indicated by the dashed lines SS, figure 5.7a, and on figure 5.7c. So that's, this dashed line is the location. How about down here? So this location right here is the same length as this original width between these two cross sections. And so this location, wherever it happens on here, we're going to put it onto this diagram. And then we're going to put our axes there. Cool. So, and this is called the neutral surface of the beam. Its intersection with any cross-sectional plane is called the neutral, what does this say? Its intersection with any cross-sectional plane is called the neutral axes of the cross-section. For instance, the z-axis is the neutral axis for the cross-section of figure 5.7b. So 5.7b, this z-axis is also, so the x and z are along the neutral, you know what I mean? So I guess it just says if we're in 2D world, and this is where I'm placing my neutral axes. then it's sideways. It's a plane. So this z-axis is also. So the z-x-axis is a plane that's cut through the neutral part of that beam. All right, sweet. Cool. So the planes containing cross sections MN, that's that slice on the left, and PQ, the slice on the right, in the deformed beam intersect in a line through the center of curvature of O prime. So if we say these lines do, because it crunches in, stretches out, these lines change, they call it change, they rotate. And so these two lines, if we extended them, meet at this point. So you extend them up and you meet at the center of a circle, and we're calling that capital O prime. Cool. And that's going to be the center of curvature. The angle between these planes is denoted by d theta. We talked about that. And the distance from O prime to the neutral surface, SS, is that radius of curvature rho. We talked about that. The initial distance, dx, between the two planes is unchanged at the neutral surface. So the distance dx between the two planes. Okay, yeah, so that's interesting. They're just saying that, I don't know what came first, but if this is where that neutral, if this is where that length that's the same, dx is, this distance right here is the same as up here. So that's what they're saying. Some of these, though, is just like, you know what I mean? I don't know if you just prove it from like a no-duh perspective or what. So, I don't know. Yeah, it's kind of interesting. The whole premise of this is like a moment. That's where I break it down into like four little elements that are getting compressed and lengthened, and I can for sure visualize that. Cool. So the initial distance dx between the two planes is unchanged at the neutral surface. Hence, rho d theta dx. Sorry. Yeah, rho d theta is equal to dx. This equation just never pops for me. It feels like I'm going to fail out of school. But your angle's in radians. And so there's no difference here. What I would do is, like, anytime that you're struggling with radians, try to just make it degrees. And then this is part of a circle. So draw the whole circle. And so if this is dx, and we drew a full circle, and we knew its radius was rho, what do we know about that circle? We know its circumference now. We can say that a circle has a circumference of pi d, and d is 2 times the radius. So the circumference is 2 pi r. Or just 2r times pi. And so if I know the radius, then I know the circumference of this circle. And then I know the angle. Let's say the angle is just 1 degree. Well, I know the circumference of a 360 degree circle. So the circumference, this part, which I just call arc length, would be 1/360th of that. And then there you go. Then you have this distance. If I know the angle and I know the radius, I know a radius is part of a circle. I would know the circumference, and I would take this angle in degrees and divide it by 360 and multiply it by the circumference of the circle. So that's going to be the fraction. Whatever angle this is divided by 360 is going to give me the fraction. It's going to multiply. That's going to be the fraction of the circumference, or you could think of it as percentage as well. The percentage is the percentage of the circumference. Now, when we deal with radians, what radians says is that if this is the radius right here, so I'm saying this is rho. I see where this picture is. I had a hard time. It's just like, yeah, this means that, hey, we can't we don't have physical enough room to draw the center of this circle in, and so we just come here and then we cut it, and then we just pretend like, hey, it goes on for a while, but at a certain point these two lines come together, and they do so right here, and then so that's where we just cut away that whole section, and then so here's the end of it. So my bad, I thought this was just a smaller picture. That's where I kind of struggle with, just like, I don't even know what you're looking at. So still, if I had to go from, so the whole distance row would be from here all the way to here. So I'd go from here to there, and okay, yeah, but let's just use this little picture. Let's pretend this is dx, and this is the radius. And this is our angle. What radians say are, and then let's have a circle that goes around like this. What a radian is let's cut a string, the distance of this radius, and then drape it around this circle. We'd get to about there. And we'd get about 60 degrees. And that's the angle. The angle that's formed right there is going to be 1 radian. And so the fact that 1 radian is associated with the length of the radius, then, you know what I mean? You have this, it should make the math easier, and it does, but it also makes it a little bit confusing. So how many angles does it take to go all the way around the circle, where we keep cutting we keep cutting these strings the length of the radius, and we drape them around? One gets to about 60, the other gets to a 120, the third one gets to about 180, and so we have 6 strings to basically get around the circle, and it's 6.2 ways, 2 pi radiuses to get around the circle. Cool. So with that, if I know my angle is 1 radian, what is this arc length? Well, it's just equal to the radius. So that's kind of the cool thing about using radians, is I for sure know my arc length. And what's the equation of the arc length from that? The equation of the arc length is 1 radian times the radius. You know what I mean? So if I had 2 radians and I was out to about 120 degrees, the arc length is going to be 2 radians times the radius. And that's going to give me this arc length. So even just right here, when it gets smaller, I don't know why it gets just a little bit harder to see, but if this is my angle in radians, then this arc length is the angle in radians times the radius. Because I'm going to have, let's say this was just 0.1 radians. That means that I'm not swept out about 60 degrees. If I cut this radius and draped it around the circle, that's 1 radian. I'm only cutting 1/10 of the radius. So I'm just cutting 1/10 of the radius and draping around the circle. So yeah, that's kind of a good way to visualize this. Is if this said 0.1 radians, well, let's take the radius and cut it into 1/10, and then start draping that around the circle. And this arc length would be 1/10. So that's like, it's synonymous. So whatever this number is, let's say it's 1/10, I'm going to multiply it by the radius. That's 1/10 of the radius. And that's going to give me this arc length. So it's good for me to just over-explain radians, radius, and I think I'll always do that. That's the one that I started. It's just like, there's no reason not to go over that every single time, because this equation comes up so often, and I just think it's visually difficult to see. And so I use the axiom, is this is the radius, and this is the radians. Radians, I say radians times radius is something normal, that's arc length. Because when we work in dynamics, we get radians per second. That's going to be the letter omega. And radians per second times radius gives me tangential velocity, gives me something normal. And then angular speed is radians per second per second. radians per second squared. So angular acceleration is the Greek letter alpha. And so if we have angular, if we have radians per second times radius, that gives me something normal, and that's the tangential acceleration. So those are the axioms that I use. Radians times radius gives me arc length. And I guess arc length is something normal. I mean, and we typically use ds for arc length, or s. So if I say the radius is r, the angle is theta, then the arc length is s. If I say the radius is r, the angle is d theta, then I'll say the arc length is ds, because then I'm ready to integrate and add up all the d thetas and make one arc length. Cool. And in this, I guess we haven't even talked about it. They just said that this dimension is dx, and when we curve it, it's still the same length. But if this is, like I just said, if this is an arc, part of an arc, we're going to give it the letter s. And so radians, theta times r, theta times radius is arc length, and that letter is s. So d theta times r is equal to ds. And so we should have the equation also that radians times radius is arc length. So we have d theta rho is equal to ds. But ds and dx are the same because we know that there's a point where those don't change that length. Cool. Okay, so finally we got past that equation, but I think that was pretty good. All right, so now, however, all other longitudinal lines between the two planes either lengthen or shorten, thereby creating normal strains. So we have this relationship that the radius times radians times radius is that arc length dx, and this should also give us every other length, though. I mean, even just from that equation, all we have to do is just change the radius a little bit. Because if I said the radians, so this is radians times radius is dx, well, let's just say this radius is half, rho divided by 2. So I'm going to take radians times half of rho, and that should give me half of dx. So so cool. So that's that gives me this length as a function of the radius. All right, keep that in mind because this whole idea is come up with an equation of y, and I really don't even know how they do it, but we'll see. And I should just read the text and see how they do it. All right, so it says, however, all other longitudinal lines between the two planes, so either lengthen or shorten, thereby creating normal strains. Cool, so yeah, the top crunches, the bottom stretches. To evaluate these normal strains, consider a typical longitudinal line EF. So now we're just going to be at this line EF, and it's going to be a distance y from the neutral axes. Cool. We identify the line EF by its distance y from the neutral surface in the initially straight beam. Okay, so we do that in figure 5.7a first. So let's look at that. So right here, we first make line EF a distance y from the neutral axes. And then we observe it down here. And so what happens is that this distance EF was the original distance dx, but then on this new picture, this distance from here to here for sure shortens, because if we extrapolate and we made this distance EF up here, it would almost be 0. And so so that's what they're going to be pointing out. All right, so that's thus we are now assuming that the x-axis lies along the neutral surface of the undeformed beam. So yeah, that's part of the, where we choose that axis has to be along the neutral axes. Of course, when the beam deflects, the neutral surface moves with the beam, but the x-axis remains fixed in position. Nevertheless, the longitudinal line EF in the deflected beam is still located at the same distance y from the neutral surface. Thus, the length L1 of the line EF after bending takes place is, just the equation that we you have to come up with on your own, you know what I mean? Derive from your own. There's a few methods to do that. I like the guess and check first, you know what I mean? Throw in a value of 0, and what should the length be? Well, rho d theta. It should be dx, and that's, yes, so that's the same thing. Rho d theta is dx. Radians times radius is arc length, and the arc length is dx. So, and over here, if I throw in a value of y is 0, then the length is dx. I think from here, this was a little bit worded not very, it was just kind of weird. So we identify line EF by its distance y from the neutral surface. That's figure 5.7a in the initially straight beam. Cool. Thus we are now assuming that the x-axis lies along the neutral surface of the undeformed beam. Yeah, so we have to say that after bending, we have a neutral surface right here. And that's where I'm going to place my x-axes and my y-axes. So before bending, I have to put my axes where that neutral surface is going to be. So, of course, when the beam deflects, the neutral surface moves with the beam. That sentence just says, hey, the neutral surface is where it is. When we bend it, it's in the same location. The neutral surface moves with the beam. Yeah, and I guess when they're saying moves with the beam, because we have a curved surface, I can't just say this is my x-axis this direction, because I think, don't we get into that on this one? Not really, but that comes up a lot, is like the x-axis. If I have this as my horizontal cut, if this is my cross-section, my x-axis, if this is the y direction, my x-axis has to be 90 degrees. So it has to be this direction. So this is my x-axis, where my x-axis can't just curve along a curved path. The reason my x-axis can be, it is perpendicular and everything still works out, which hopefully they mention, is because this curved line is the, if I projected that down on the x-axis, that line is going to be the same length. You know what I mean? If I project it straight down, this line will be a little bit less. But yeah, so so that's something that happens also in chapter 9, is that even though moments cause a lot of deflection, the deflections are still very, very small, especially within the linear range. Things don't move very much. They can move a little bit noticeably with bending, but still those deflections are small enough where we just assume that the x-axis kind of follows this line just in general. Even though it's 90 degrees, it's tangent to this point at that cross-section. Okay, so of course, when the beam deflects, the neutral surface moves with the beam, but the x-axis remains fixed in position. I'm glad I went over that, because that's exactly what I just said, is that the x-axis has to stay in position. The neutral surface will move upward. It'll deflect up, but it's no longer along the x-axis. Nevertheless, the longitudinal line EF in the deflected beam is still located at the same distance y from the neutral surface. So I guess if we're looking at this cut MN, I think that's what they're saying. If we look at this cross-sectional cut MN, this line EF is at a distance y, and same thing here. And is that what they're saying? I mean, do they even say the section MN in particular? not necessarily, you know what I mean? So, yeah, it's just at some point they might talk about how the deflections are small. We'll see if they do. Okay, so just know that the x-axis remains fixed, and the curved surface, yeah, we still take the y value from this neutral curved surface wherever we are. You know what I mean? And visually, it might be better just to put it over here. But now, I guess you got to put it right here. I mean, just anywhere between here and here. Just knowing that this deflection, this angle that gets formed is small. It's a d theta, and then and if the x-axis is at a 90, that this variation isn't very much. All right, so that kind of pops out of just that sentence. That's why reading textbooks is a little bit tricky. Nevertheless, the longitudinal line EF in the deflected beam is still located at the same distance y from the neutral surface. Thus, the length L1 of either line EF after bending takes place is this equation, in which we have substituted. So right here they substituted d theta. Well, I guess they got the equation from. Yes, it's so fascinating that I first got the equation by saying, hey, if this is dx, then the equation should be is when y is rho, it should be 0. So I'm going to have dx minus y divided by rho dx. You know what I mean? So I think you can just get there. And you can do that from slopes of lines. You know what I mean? If this is my x-axis and this is my y-axis, well, let's see. Oh, yeah. So if this is my x-axis, this is my y-axis, where this goes through, the y-intercept is at y. So then the equation of a line is y is equal to mx plus b. The y-intercept b is at a distance of rho. And then the slope. Well, the slope is hella negative. And the slope is just rise over run. So the rise is rho, or negative rho, and the run is dx. So that's the equation. So our equation for this line, oh, but yeah, that equation doesn't give the length. So what we want to know is the x value. So we got to tip this onto edge. So what I would do is change my variables, and I would say, like, this would be the y direction, and then let's say this is the x direction. And I think this is a good tool. I mean, it's good mentally to flip your axes. It's when we need an equation, I need to know, and then, because any equation, if this is the y-axis, and this is the x-axis, and I have a line along, a equation for a line, any value of x gives me the height, or gives me that value of y, which I can say for this is a height. And so if my value of x is 0, my equation for y, for the height, should be dx. So that's where I'm going to have y is equal to at least dx. And then for this equation, if this is y, then my y-intercept is dx. So if my equation for a line is y is equal to mx plus b, the b part is dx. And then the slope, if I'm saying this is the y-axis and this is the x-axis, then my slope goes negative. So let's see. And so the rise over run would be, the rise would be dx, and the run would be rho. And so that's going to be a negative dx divided by rho. So heck yeah. So so that's our slope, negative dx divided by rho. So we have y is equal to mx plus b, and b is dx. So we have y is equal to, and the slope is negative dx divided by rho. And so we have y is equal to negative dx rho, and then and this value for x. Now the only thing here is now we gotta say we just came up with the equation for a line where we're saying this is the y-axis, but for this we're saying that this is the y direction, but the y direction is our independent variable. You know, when coming up with an equation for a line, this is your y-axis, this is your x-axis, where I'm going to just throw in an incremental value of x, and I want to pop out the height of a line. I know that height of that line might vary, but the x-axis is my independent variable, where here my y is my independent variable. So let's do this again mentally and see if we can just do it in one go. So my x-axis is going to be, very similar to my y-axis. So let's not think about that anymore. But heck yeah, so my x-axis is my dependent variable. My y is my independent variable. Slopes will be in the x direction. It'll be change in x divided by change in y. So the slope is going to be the opposite of what we're familiar with. The x, where this line intercepts the x-axis, and the x-axis is the dependent variable, that's going to be the x-intercept. And now we want an equation that's x is equal to mx. Sorry, we want an equation that's x is equal to my plus b. So yeah, this is difficult for me just to mentally do, and this is where I should have paper, but I think mentally we can get it, and I do a good job of just juggling my way through here. So hell yeah. So the equation for a line is just x is equal to my plus b. That doesn't sound too hard. And the x-intercept, or the b part of that equation, is dx. Is that right? Heck yeah. That's where, when we throw in our independent variable is y, when we throw in a 0 for that, we're going to get the x-intercept, dx. And then our slope is going to be negative dx rho. So cool. So we have negative dx rho y plus dx. And that's our equation. Negative dx rho y plus dx. So that wasn't too hard. So we have negative dx rho. So that's why I was saying negative dx divided by rho. I should have said divided by. Negative dx divided by rho y plus dx. So even just right here, I wish textbooks, and I should throw some asterisks on my sheet of paper that I don't have, and makes, I do enjoy making these longer videos, because just in the long game, if I'm going to do this, let's say I was going to do this for the next 20 years and get no better. You can get slowly better. So why wouldn't I, struggle through the things that I struggle with? Which even just right there is just and these textbooks, it's why don't they go over that, hey, the equation for this line, they just assume that you know that. And I swear, even the basics of finding the equation of a line, when it comes to this geometry in this setup, that's the hardest thing for engineering students, because you're just that's not covered in this section, but then it's a piece of math, and it's the worst piece of math because it's fairly simple. And the simpler it is, the harder it is. If you're integrating a rectangle, using the integration dA, integration dx dy, that can be more daunting than integrating the area under the curve of an x squared equation, just because you spend 0 time integrating areas under curves of rectangles, but you might spend time integrating areas under the x squared or parabolic or it's interesting when math terms, did I say that right? Is x squared, what do they call that, a parabola? Yeah, parabolic. Sometimes the definitions, it's like saying bread 1,000 times. You're just is that, what are we talking about? Cool. All right, so we got the equation of that line. And you know, I don't like this. I don't like how people do equations of lines where you're just like, this should be this should be negative dx divided by rho y plus dx. That's going to be, that means that y is my independent variable. That means that x is my dependent variable. So that means that the graph is 90 degrees rotated from what we're used to, you know what I mean, in high school. And so this is my x-axis, this is my y-axis. It's even rotated, and it seems like it's even inverted, you know, to mentally do that. And then so here's the equation of the line. And I want to know the height, x. The x is my independent variable. I want to throw in a value of y and then output a value for that height. And that's going to be my value for x. And so, hell yeah. So this equation should be x is equal to my plus b. X is equal to negative dx divided by rho times y plus dx. And booyah. So that's the equation. They get it from the idea that if we throw in radians times radius. So radians times radius is arc length. So if I throw in d theta rho, gives me dx. But then if I throw in d theta rho minus rho, hey, that's going to give me the point right there. It's going to be 0. So then I can throw, and that rho value is my y. So there you go. So that's probably simpler. Now I can see how that's kind of simpler. This neutral place is going to be radians times radius is this arc length. This is, sorry I'm juggling on this, but I always like to take, you know, another value that seems, another place that seems obvious. Like the arc length right here is 0. So that's going to be radians times radius minus my y value, where my y value is the radius. So I'm going to do radians times radius minus radius gives me a radius of 0, and then that's going to give me an arc length of 0. So that equation would be d theta times rho, d theta times parentheses rho minus y. And so that's how they get this equation. Is, hey, rho minus y is just my, and now I see it even simpler. You know what I mean? So rho minus y is just the radius at any point along here. So if I was halfway, the radius halfway is just rho divided by 2. And that's going to give me half the distance. But if I have to start with this variable rho, I got to go rho minus rho divided by 2 to get that length. So yeah, rho minus y. So if this, so starting here, I guess, if my y values start here and I go up a distance y of rho divided by 2, my radius is now rho minus y, rho minus rho divided by 2, which gives me half the radius, half of rho, and now my angle is still d theta. Radians times radius is arc length. D theta times rho divided by 2 gives me that arc length when I throw in a y value of rho divided by 2. So let's go back to the equation. If I throw in rho divided by 2, 1 rho minus half of a rho is half of a rho, and I get half of a rho d theta. And if I know rho d theta is dx, that's going to give me a half of dx. Let's throw it in right here. If I throw in y is equal to rho divided by 2, this is going to be dx minus, the rho's cancel, and I'm just having 1/2 dx. So 1 dx minus 1/2 dx is 1/2 dx. All right, so I'm enjoying spending so much time on just this linear equation because you can get to it in 2 different ways. One using radians times radius is the arc length, and that arc length will be the length of that line. where here is just linear. This is actually linearizing it. This is more accurate, where this is turning this into a linear. This is saying that d theta is so small that this 90-degree axis is basically in line with this dotted line, even though that dotted line is curved. So we'll see if they do talk about that. I'm sure they do talk about that. And then so here, using the radians times radius approach, then what they do is they substitute the fact that d theta is dx divided by rho. And just from the fact that rho d theta is equal to dx. So if you get a relationship, this comes up a lot where it's just like, hey, I have 3 different things here. I could change any one of them, and or I could rearrange this equation 3 different ways. I could solve for d theta, I could solve for rho, or keep it in this form, solve for dx. So here we have a d theta. So let's come up here and let's solve this for d theta. Well, d theta is going to be dx divided by rho. Cool. So I can do that, and I'm going to say d theta is dx divided by rho, and then I can just plug that in. So I'm going to have dx divided by rho, and then as I factor that through, I'm going to have rho divided by rho times dx. That's rho divided by rho is 1, so I'm just going to have that dx term. And then I'm going to have negative y dx divided by rho. Negative y dx divided by rho. So there you go. So we have that. But yeah, still, this is, this isn't an approximation. So it's very fascinating. We say that we have this distance dx before we deform it. And then when we do deform it, well, there's still a line, a curved line that's going to be a distance dx. Now, this line is now curved for sure, but that curved line has a distance dx. That dx is equivalent to ds. You know what I mean? So those are the same, identical for this. There's no approximation there. And yeah. And so, so, and then even finding these arc lengths, this isn't a linear, even though we're using kind of a linear equation to do so, there is, we're just using, the linear, it would make no difference. It would make no difference if I straighten this line out to here and called it dx, and then drew my line all the way to the center. The equation for that line would be the same thing as curving this line and then saying, at the halfway point, this is going to be half of dx. So, so one is a bunch of curved lengths, but they reduce linearly. If I get halfway, this gets halved. If I go all the way to the center, there's no more length. Compared to if I just made this a straight line that was dx. So yeah, that is fascinating. So maybe that is probably why, that you're not using just a linear equation that says y is equal to mx plus b, or x is equal to my plus b. Because we're using radians times radius. If I know this d theta, radians times radius is this arc length. And if I reduce that by half, my radius halved, and now I have radians times half my radius, well, that must be half my arc length. So hell yeah, kind of just learning on the fly, so that's good. So there is no, on this one, there is no, I guess there is no small angle approximation or anything like that. All right, hell yeah. I thought we were going to get through the example, but I don't think so. I think we'll do that example for another time. It's just good to do the proofs, but we'll see. All right, so since the original length of the line EF is dx, it follows that the elongation is L1 minus dx. So now we're going back up to here. We want to know how much this elongates. And we're using the term elongation for shortening and lengthening. And so this for sure shortens. So we're going to have a negative elongation. And we know the length of this line from that equation that we got. And so what I want to know, because we're trying to find the strain, if I know how much it changed length, that is going to be useful. But the strain equation, let's go to the strain equation. The strain equation is a change in length. It doesn't really have it on here, but strain equation is a change in length compared to the original length. So if this original length, I always like to use 1 meter because I can break 1 meter into 1,000 millimeters. And with steel, it can only lengthen or shorten by 0.2%. That's going to be multiplying 1,000 by 0.002, which gives 2 millimeters. And so if this line shortens by 2 millimeters, if this is 1 meter long and this shortens by 2 millimeters, that tells me the tension in this steel can only compress or have a tension up to 58,000 pounds. And so that's how that's synonymous. If I know the change in length compared to the original length, then I know, and how that, and if that's 0.2%, then I know the pressure in here is 58,000 pounds. And so I can't just know the change in length. So if I say this had the original length of dx, and then I can get the length of this. Even just the length of this doesn't tell me anything. But the difference between lengths, well, the change in length, that still doesn't quite tell me anything. I have to get the percent change in length. So let's just visually do this. So I can visualize this length. I can see it. Now I can visualize this length. Do you think this length is 90% of this length? I don't know. Do I think this length is 50%? Hell no. We talked about where the 50% point was. And so I'm going to say it's, 90 to 95% the length. And so that means that the change in length was only 10% or 5%. So let's say this change in length is 5%. Cool. So now that gives me something to work with, because I said if this was steel and something had a change in length of 0.2%, then we're basically, at the limit. So this picture is highly exaggerated, and that's good to point out, where we have to use highly exaggerated pictures to show these curves, to show these changes in lengths, just to get a mental idea of what's going on. All right, but again, it's not the change in length that's important. It's the change in length divided by the original length. And that's going to give me basically the percent change in length, or the fractional change in length. If this change in length was compared to the original length was 0.1, then I know that, and let's say negative 0.1, then I know it reduced by 10%. So that's a better way to say that. Cool. But yeah, I just think the second you get into this word strain, the name sounds awful. Epsilon, that's got to be the most hardest Greek letter in the whole alphabet. I mean, just to look at. Visually, it's difficult to look at, and makes sense that you'd even want to use it. But yeah, those two things. The fact that strain, like if you strained or sprained your ankle, I don't think there's any difference between those two. Yeah, you'd kind of have to look up the Latin, where the hell does strain come from? But it must mean a change in length, because that's the whole idea. But yeah, the hardest part about material mechanics is like we don't associate that. I don't just say, "Oh, looks like I can totally tell you pulled on that steel cable, 2 millimeters. So it looks like the force that you applied is yada yada." We just don't do that. We have no association with that. It looks like, hey, it looks like you're stretching that cable with your truck, trying to pull out that tree root, and so I kind of know the forces that might be in play. I don't do the opposite. I don't be like, that cable looks like it's stretched. In a steel cable, that's a horrible analogy anyway, because the cable is all loose. You know what I mean? You'd have to have a steel rod. If you're just like, oh yeah, so I see that steel rod that you're pulling on lengthened fractions of a millimeter that I can't even tell. But if I could tell, and I could measure that, I could tell you the force being applied to that rod. And so, yep, and so that's how that is synonymous. That's the whole reason we're trying to get this relationship with strain, because then we'll just be like, cool, we know the strain, therefore we know the pressures, because this relationship, because we pull on materials and we see that they change in length, and those change in lengths are associated with pressures. And I just say general change in length, but we know now that it has to be a fractional change in length. It has to be a percent change. That's where steel can induce a 0.2% change in length, or a fractional change in length of 0.002 compared to the original length. And other materials are going to be a different value for that. All right, hell yeah. So now we're into talking about finally strain. All right, so we got that equation. Where are we at? Did we even get down here? Yeah, so thus the line L1 after the length of the length L1 of the line EF. So yeah, we have an equation anywhere we throw in a value of y. So we're saying L1 is where we throw in this value of y. And I guess, this value y could be anything, but for this diagram, y is up to EF for that. You should call it y1 if you're just talking about EF right here, but maybe not. No, never mind. Forget I said that. But yeah, we have an equation for any value of y. We're just analyzing when y is y. We're going to be at EF. So right here, the length of L1 is going to be dx minus y rho dx. So that's why this should be the length of, this should be L bracket y. The length of any arc at any value of y. So that's why I don't like that either. They're just saying L1 is this length EF, but because we have an equation, we know every length. We know the length at at any value of y we want. So that length EF is this equation, and the change in length. So now that we know that, the change in length is going to be the original length. Back it up. Change in length is length final minus length initial. So if my length final is shorter, and then I'm subtracting a bigger number, that's how I get a negative change in length. So we're going to find change in length, which is length final. That's L1. That's that equation, minus dx. So if we come back to this equation, we see that this equation is dx minus y rho dx. That's our final length, and then we're going to subtract the initial length. So we're going to subtract dx. So these dx's cancel, and we just get negative y rho dx. So that's how we get. Now that's just the change in length. So like I said, so that gets us closer, but strain is change in length divided by initial length. Because if I have a 1 meter, 1,000 millimeter steel bar, and I lengthen it 2 millimeters, hell yeah, I can do that. It's right at the limit. But if I have a 0.5 meter steel bar and I lengthen it 2 millimeters, well, now it's deformed. So the change in length compared to the original length is important. That gives you the percent change. That's why if you say steel has a percent change in length of 0.2, it doesn't matter if it's the Golden Gate Bridge or like a climbing carabiner. No little segment on that steel can lengthen more than 0.2%. Cool. So, hell yeah. So strain is change in length divided by original length. So the original length is dx. So let's talk about this before we do the equation. We know this equation. Hopefully we can do it from memory. It's dx minus rho divided by y dx. And it's just good to like have an equation and kind of get familiar with it. And so we're going to say length final minus length initial. So the dx's cancel, and now we just have negative y divided by rho dx. That's the change in length. The change in length divided by the original length, the dx's cancel. And so strain is negative y rho. So now let's talk through that again. So the length at EF is this equation. This is length final. The original length was dx. So we're going to subtract length final minus length initial. This minus dx. The dx's will cancel, and we just have this, negative y rho dx. That's the change in length. Strain is change in length divided by original length. So we're going to divide this by the original length of dx. The dx's cancel, and strain is negative y rho. But I think this one is a difficult one because it seems like a lot cancels. We pick up a rho. We have a value of y, which should be good, but it's just bizarre having y as our independent variable. So that is kind of tricky, you know what I mean? But what we have here is any value of y, we go in the negative direction, we're going to have the strain. But then it's also tricky because no human, besides humans doing material mechanics, ever think of a change in length being associated with the load put on something. No one's, because you can't see it. Usually the change in lengths are just small and you're not going to notice it. But if you're, and then it's worse because let's say you're torquing a bolt. Well, you can easily over torque it and then you're just into plastically deforming it, and sure, you lengthened it. And so up to the point where you're getting that max pressure that you can put in things, that change in length is very small and imperceptible when it comes to most building materials, steel, wood, concrete. And so that's just a bummer. All right, so hell yeah. So and again, y is our independent variable. I can come up to this top surface and I want to know the strain. I really don't want to know the strain. I just want to know the pressure. All material mechanics basically boil down to, hey, if the pressure up here is greater than 58,000, and in this case a negative compression force of 58,000 pounds, we got issues. You know what I mean? So every material has a max compression, it has a max tension, and a max shear pressure. The general gist of material mechanics is like, hey, if you can identify a location that's based on geometry and forces that's going to have a number bigger than that, well, you better design it just a little bit bigger. You know what I mean? Double the size of the darn thing. So yeah, that's just kind of material mechanics in a nutshell. But, the fact that strain is a bizarre term, it's a change in length divided by initial length. That percent change in length is really small. At least steel is 0.2%, but as a fraction, that's 0.002, and it still gets difficult to work with in equations and get mentally familiar with. All right, hell yeah, but we did it. So we have this value of strain. Now the light bulb should go on and be like, yay, but it doesn't because it's just really difficult as humans to be like, hey, a change in length, a percent change in length can give me the load. So, I mean, we're just going to kind of end it at this section 5.4, but the next section, if I have another 2 hours to burn. No, I do. I'm just doing this because I can get better at teaching. We're going to say that, hey, look at this. That strain is associated with stress. Stresses are really, and then stress is basically like load. You know what I mean? So when we do have a specimen and we load it, if I have a 1 inch by 1 inch steel bar, and I put a tension on it of 58,000 pounds. The surface area is 1 square inch. The load is 58,000. The pressure I'm putting on that cross section is 58,000 psi. So that's this term, and that's the max I can put on it. What I'm going to see if that bar is 1 meter long, I'm going to see a lengthening of 2 millimeters. So that's going to be 2 divided by 1,000, which is 0.002. So if I put 58,000 in this side and 0.002 in this side. And what is 0.002? Well, if I had 0.2, because we're in decimal world, if I had 0.2, that's going to be 1/5. So I basically have 1 divided by 500. Is that even right? Is it 1 divided? See, I'm so bad with decimals. Is if 0.2 is 1/5, is 0.002? Isn't that just 2 more swipes? Isn't that just 1 divided by 500? Well, then I would take 500, multiply it up here, and I would get. I do not like this. Bummer. So yeah. So stress in steel is 58,000 pounds. That's the max tension you can put on it. The max strain is 0.002. So if I have a very small number equaling to a pretty sizable number, this number has to be way big. So this number is 29 million. And so if I have 29 million times 0.002, 29 times 2 is 58. And then 29 million, but this is 0.002. I would move the decimal place 1, 2, 3, and so my 29 million becomes 2,290,000. 29,000 multiplied by 2 is 5,800. So that's how, using this equation and throwing steel in there, and knowing that steel has a pressure of 58,000. And the strain can be 0.002. This number is 29 million. And all you're doing there is just relating the fact that if I pull on a chunk of steel and load it, I'm going to observe a change in length. But I'm not always going to have a 1-inch rod of steel that's 1 meter long. I might have a 1-inch rod of steel that's a lot longer or a lot shorter. I might have a 1 meter chunk of steel that's real thin, just a 1/4 inch, in diameter or something like that. And so what we need is the pressures. The pressure is going to be the same. 58,000 psi as a pressure. That is going to be the same as that thing stretching 0.2%. Or 0.002 times its original length. I don't know, maybe this is just a garbage way to teach. I don't think so. I think just keeping reiterating what these terms are, because people, like I at least got to fail this class and redo it. And even after going through it the second time, because it gets so detailed of using complex equations that get more and more complex, I lose touch of the fundamentals. But the fundamentals are this whole idea that materials, have linear properties, but they're still empirical. Like we pull on something with a load and we measure its change in length. And so, but the cool thing, at least that's a linear relationship up to where the material is kind of past its prime and things might fail. So that is a useful thing. And I will just say, I need to look up why that's linear. I find that fascinating because molecular interactions are due to electrons, charges. Like everything in the, from that perspective is forces based on charge. Except gravity, we just don't know what gravity, that's the only one that's not based on charge, or one of them that isn't. But yeah, so electrostatic forces wouldn't vary linearly. So I just find that fascinating. But like I said, these distances that we're pulling on stuff are not very far. So it's linear just for a very short range. So I'm going to ask my brother that, because he's a quantum physicist, to be like, if you have electrostatic charges, an electrostatic charge that, fades with the distance squared. Two magnets, if you double the distance, will have a fourth, will reduce in force by 4. You have that inverse squared. And that's the same with gravity. So yeah, and that's the most fascinating thing in my wheelhouse, this week, is just like, you do have this very bizarre linear relationship when things move very subtly. Yeah, so I find that super fascinating. Yeah, so anyway. All right, so we are almost... and so that's going to be section 5, is being like, hell yeah, we want the pressure. We really, you know what I mean? Like I said, humans, I don't think the word strain is in our wheelhouse. Even if you're doing this as material mechanics, you're just like, hell yeah, stress, shear stress, normal stress. Yeah, you want a 10-foot pole strain, but this is one of them where we use geometry to show a change in length. If we know change in length, we know strain, and therefore if we know strain, we know the pressures. Cool. All right, so we get this equation. We get strain is equal to negative y rho. We can throw any value of y in and get the strain. And I don't like this because then, why not just leave it like this? But we have to throw in this extra little term called curvature, and we're going to say curvature is just 1 divided by rho. So that was the last section. I guess we can handle it now. Curvature is going to be positive when rho is a positive value. We can say rho is a positive value if this origin of the circle is in the positive y direction. If this is curving this way, the origin of the circle is down here, and that's going to be in the negative y direction. I'm just going to say rho is a negative number. If you do that, you can't go wrong with the positive and negatives on curvature. And I think that's a pro tip right there. Alrighty. Sweet. So yeah, so we have strain is equal to negative k y. So this is curvature, negative curvature. And then we have y. Cool. And hell yeah. So the preceding equation, that's this, shows that the longitudinal strains, so the strains in the x direction. So now we say, hey, strains in the x, along the x-axis, at a value of y. So they're going to vary. When I throw in y is 0, there's no strain. So cool, we can do that. That's the first thing to do in an equation, is find maybe the 0 point. So hell yeah. So when I throw in a value of 0, there is no strain. Strain is 0. Change in length is 0. Stress is 0. And we'll do that in section 5.5. Cool. And then so this little x is being, this says that if this is the x-axis, if this is the x direction and this is the y direction, our cross sections are at some value of x. So we're going to say at some value of x, I want to go up into the y direction, and I want to find the strain at that point. So that is what that's saying. I think that's good to go over. So this is the strain at some value of x. When we go up into the y direction, we're going to get a strain at that point. It's not a function of z, so it's going to be, if we move in the z direction, or move in and out of the board, the strain widthwise is going to be the same. Cool. If the curvature is, so what we got? So the preceding equation shows that the longitudinal strains in the beam are proportional to the curvature and vary linearly with the distance. So hell yeah, the distance is 0, strain is 0, distance is a little bit, strain's a little bit, double that's double it from the neutral surface. When the point under consideration is above the neutral surface, just above the neutral surface, the strain, so the y is going to be positive, strain is going to be a negative value. So that's what we have here. So we have, we have two different things. When the curvature is positive, so we have this negative, and we have curvature and y. Any of these two things can be either negative or positive. So when we go in the positive y direction, if curvature is positive, that's what our diagram is, positive, positive, negative. Our strain is going to be negative and therefore crunching in. If our curvature is negative, we just flipped it this direction. My y direction is still up, and so this is going to be a positive y, negative curvature, and a negative sign. So negative, negative, positive. that's going to be a positive value for strain. And so if we have a curve this way and I go up in the positive direction, we're going to get tension. We're going to get an increase in length. The length's going to lengthen. And I could also go, I could do the other two. Let's do them. So let's go back to the smiley face. We're going to have a positive curvature. I'm going to go in the negative y direction. That means that below the neutral axis, things are going to be in tension or stretch out. Strain is going to be a positive stretching out. So I'm going to have a positive curvature, negative right here, and a negative y direction. Negative, negative, and then this positive. So we have overall positive strain. Okay, now let's do the last one. We have negative curvature. K is negative. We're going to go in the negative y direction. So we have negative, negative, negative. That gives me negative strain. And if I have a curve this way, in the y direction, we're going to have crunching in of that beam. So yep, so that jives. And there's kind of 4 different ways you can look at this equation. I think that was really good to go over. All right, so when the point under consideration is above the neutral surface, the distance y is positive. If the curvature is also positive, you have positive, positive, but the equation is negative, then Ex will be a negative strain in compression, representing a shortening. By contrast, if the point under consideration is below the neutral surface, y is negative, the distance y will be negative. And then the curvature, if the curvature is positive, you're going to have negative, positive, but the equation is negative. So negative, negative, positive, you're going to have positive strain. The strain Ex will also be positive, representing an elongation. And so let's visually do that one. If the point under consideration is below the neutral surface, if we have this and we're going below the neutral surface, y is negative, the curvature is positive, the strain is going to be positive. It's going to be stretching out, representing an elongation. Note that the sign convention for Ex is the same as that used for normal strains in earlier chapters. Okay, yeah, so it's axial strain. So it's at a cross-section X. We're going to get a strain, is that what that's saying? Strain in the X, longitudinal. I'll have to, anyway. But it's also parentheses as a function of y. This strain Ex, parentheses, is a function of y. So if this is a function, f is a function of something, this is f as a function of y. Y is our independent variable. So we have epsilon x parentheses y. Strain is a function of y. We can vary y, and cool. Given a curvature, given a known curvature, yep. Yeah, and this is kind of fascinating. I think, like, what comes first, the chicken or the egg? We're basically saying, hey, I think we have a curve. And we talked about this in one of my videos. Is like, why isn't, if I do have shortening, why isn't this thing just a trapezoid? Why isn't this just a flat line and this is just a longer line? And the reason is because if you do the 4-molecule test, these 2 molecules crunch in, these 2 molecules lengthen, and I could apply that moment right here and this moment right there and no other moments along the extra part of the beam. So these 2 lines would curve and this beam would just be straight that way, unbent. And so, so when we analyze that, this shape for sure is a trapezoid. It's flat on top, it's shorter, it's flat on the bottom, it's longer. That is a trapezoid. But the second we go to the next 4 molecules, that same shape is going to happen. And sure, I have a flat, but then I also have another flat. And guess what? I have a change in angle. And so that change in angle is basically the definition of a curve. A curve is just any change in angle. A circle is where your change in angle is repetitive, and we talked about that. So when we have the case of pure bending, that next trapezoid is going to be the same shape. So this flat to this angle is going to be defining a circle, because the next one is also going to be the same change in angle. And this change in angle is d theta, and we showed that as well. I think we should. it's fascinating how you can kind of lose things. You're just like, how do I prove that again? How do I prove that if this is a slice of a circle, and then this tangent we're just going to call 0 degrees, why is this tangent d theta? You know what I mean? That's kind of fascinating. And I like to do it from a sheet of paper. Take a square sheet of paper and put the square part right here along the x-axis, 90 degrees, and then pin it at the origin up here. And then rotate it d theta. Cool. What happens is that you rotated it d theta, and then what happened to this angle? That angle also rotated d theta. And go to 90 and just, it's super obvious. If you take this up to 90, well now that angle is 90 degrees, and your sweep, your change in angle was 90 degrees. So that is, but yeah, I think that, and I'm sure, like I'm not very good at the math of circles. I'm trying to go through my calculus books when it comes to deriving the equations of circles. Man, that stuff gets complex fast, and unless you have like a math teacher, you know, kind of like spoon feeding it, yeah, I think it can be kind of a nightmare. I mean, because gosh, this seems basic as, but I still have to double down on it. All right, sweet. Cool, we're almost there. Okay, so we just went over the sign conventions. Note that the sign convention for EX is the same as that used for normal strains in earlier chapters. Cool. Basically, elongation is positive and shortening is negative. Grab some water. Equation 5.4 for the normal strains. So what equation? Yeah, so this equation that we have. And you're basically going to use it in this form. Strain is negative curvature y, or y is your independent variable. You can go up or down in that from that neutral surface. So for the normal strains in a beam, equation 5.4 for these strains, the normal strains in a beam, was derived solely from geometry, and that's cool. That's what we just talked about. So I think that's pretty cool. You know, like I like my teaching method is like, and your learning method, especially if you're revisiting a chapter you've already read. See if you can foreshadow kind of what's gonna, like this follows that follows the next thing. I think that's a very good approach. So that equation 5.4 for normal strains in a beam was derived solely from geometry of the deformed beam. So we're just saying, hey, the beam has curve just because we observe curve. Like when we go to deform a beam or put load on it, it looks like it curved. And in between any two little points, you know, this dx points, I can actually say, yeah, that is, yeah, so let's go back to that. Just from nature, if I see a beam and it's curved, I can take a point right here and a point right here, measure the tangent, and then measure the new tangent, and be like, yeah, I think the angle changed. And I know that change in angle has to be part of a circle. You know what I mean? So those things are just geometry, and that's fascinating. But it's from that geometry I know the change in length, because I knew this beam used to be like this. You know what I mean? So, I mean, it doesn't forge, because when I undo the loads, it goes right back to this shape, as long as we stay in that linear range, and that's kind of the full strength of materials. Anyway, so hell yeah. So this is kind of a great way to end it. So those properties of the material geometry. That equation 5.4, and let's strains along the x-axis, strains in the longitudinal direction, are equal to negative curvature y. So equation 5.4 for the normal strains in a beam was derived solely from geometry of the deformed beam. The properties of the material did not enter into the discussion. Therefore, the strains in a beam in pure bending vary linearly with distance from the neutral surface, regardless of the shape of the stress-strain curve of the material. Oh, that's interesting. So it doesn't even matter the strains in the beam. Yeah, that is fascinating. That is a head scratcher, because you're just like, what if you had material that was, that wasn't linearly elastic? Yeah, it's kind of interesting. The next step in our analysis, namely finding the stresses from the strains, requires the use of the stress-strain curve. This step is described in, so that's the next thing. We use that stress-strain curve to actually find the stress, the PSI, the pressure. This step is described in the section for linear elastic materials and in section 610 for elastoplastic materials. The longitudinal strains in a beam, that's what we got an equation for, are accompanied by transverse strains. That is normal strains in the y and z directions. So yeah, that's kind of fascinating. So we're gonna have crunching up here, but check it out. What did we say? We said that if we have crunching up here, it's going to be bulged out, and it's going to be bulged out. If this is a cube, where this left face and right face, and we're just taking this slice up here. You know what I mean? So just imagine a small little cube right here where this left face and right face are having, they're being compressed together. But because it's a cube, it's got 6 other faces. And those other faces, those other 4 faces are being bulged out because this little cube is being compressed in on 2 faces. Poisson's ratio says that, hey, it must be getting bulged out in others because it's the volume doesn't just decrease 100%. It decreases for sure, but it also bulges out the side as well. So as we are visibly changing the length, if there was no bulging, that would just be a new volume. Like we're literally decreasing the volume. Poisson's ratio says that it doesn't decrease that exact amount. Some of it, about 30%, gets pushed out the sides. You know, for steel it's 0.3. And so that gets pushed out on this top face and this bottom face. That's the y direction. So this y direction increases in length up here, for that. And then the surface right here and on the other side also get bulged out. So that's the z direction. So that's what they say in the z direction. So even just reading textbooks is difficult because they spell it out, but then you got to go back and look at the pictures and be like, yep, okay, I see where that makes sense. So so up here it gets bulged out. Down here it gets sucked in. You know what I mean? Because we're pulling, we're lengthening it. But that little cube, when we increase its length on both sides, the length of this, it doesn't just increase in volume that much. It also kind of sucks in, and so we only, like 30% of it gets sucked in. You know what I mean? So is the opposite true? Like the change in volume will be 60% of the, if we have a square right here and we move this side that direction and this side that direction, it should be a volume like that, but all we see is maybe about 60% of that because it's getting sucked in on the sides. And it's getting sucked in on all 4 sides. The y direction is shortening and the z direction is also shortening. So that's kind of cool. When you get a beam that bends up like this, you get a curvature this way, you get shortening, you get that curve, but then you also get a bulging, you know what I mean, like a bread loaf, like the top of a muffin up here, and then getting sucked in down on here on all surfaces. And so that's kind of interesting. You get concave bread loaf and then convex, maybe like the bottom of a bread pan, bottom of the bread. Anyway, sweet. So that's good. And some books actually show that photo, which is a good photo to look at. Even though when you just first look at it, you're like, oh, that sounds complicated. All right, so we are almost done. So, so looking at the stress-strain curve. Okay, yeah, and Poisson's ratio. The longitudinal strains in a beam are accompanied by transverse strains. That's what we talked about. Normal, so that is normal strains in the y and z direction. So I guess they're called normal strains. I mean, they're normal to the y and z directions. And they're normal. They're Yeah, shear strains are changes in angle. So these are just, you know, obvious. I mean, normal, I don't know. They're the easier ones to, like, obviously it's getting crunched in. This volume is getting reduced, but it's also getting pushed out. So that's the same thing as looking at a side view and just saying, hey, let's pull out on this and pull out on this. Well, then that volume is increasing that way, you know, in the z direction. And if I pulled up and then down, that little volume is increasing that way. So that's what's happening in the y and z direction. And those are what we consider normal strains. They're changes in yeah, there's no angle that forms this, you know, the little cube doesn't, you know, turn into a diamond shape. All right. However, there are no accompanying transverse stresses because beams are free to deform laterally. This stress condition is analogous to that of a prismatic bar in tension or compression, and therefore longitudinal elements in a beam in pure bending are in a state of uniaxial stress. Okay, I need to read this one again because this is one that, like, I feel like I push back against. So, however, there are no accompanying transverse. The transverse directions were that y and z directions. But there's no stresses in those directions because the beams are free to deform laterally. I guess that's just the nature. I need to like, that's something where I need to read more literature on just to feel. I know that if you yeah, okay. And this stress condition is analogous to that of a prismatic bar in tension or compression, and therefore longitudinal elements in a beam in pure bending are in a state of uniaxial stress. All right, that last one, again, asterisk. There's no words that I could say to explain my way, for me to have a better understanding of why there's no accompanying transverse stresses. So I got to end it here. And hell yeah. So if you want to look at the example, I'll at least keep it here for a little bit. And then we'll go to this picture. And all right. And then the next, and here's the solution to that one if you want to see. But I'll go over that in like just a shorter video. All right, booyah. And again, the next one is taking those strains and finding the formula for stress. Cool. Yeah, it's kind of fascinating just taking like an hour and a half, 2 hours to do like one section at a time. Even though like once you get this derivation, it's good to do the problems, you know, from the full derivation all the way through. You can just do it in like four or five mental steps to go from geometry, curvature, to the strain equation, to the stress equation, from the stress equation to the force equation. Some of the forces are zero. That gives you the neutral axes. To the moment equation, that gives you the equation that we're shooting for, which is the stress is equal to the moment that you're reefing on it, the distance from that neutral axis divided by the shape of the I-beam. And so that's the stress at any value of y. And so, hell yeah. I mean, I did the full tutorial in the first one because we went over the full review, but this is just going section by section and trying to spend as long as possible on each section. 5.5 will be the next. All right, so thanks for joining me, and guess what? That's a video.